Intersecting line segments. We'll start with some basic terminology again of the intersecting line segments. At T1, A and C are comparable, but not B. At T1, A is above C. So what does that mean? What exactly can we translate these definitions to be useful when evaluating line segments and their intersections? So again, let's review. At T1, A and C are comparable, but not B. Think about this terminology. You have T1, which in this case actually represents time. This is one of the few algorithms that we'll explore in these 4 sections that actually takes time into account. All the other algorithms really deal with like fixed point sequences. Once P1, say, is fixed, it occurred, we're not really concerned about when it occurred. We just know that it occurred. So when you're looking at these intersecting line segments and using the sweeping algorithm, you're really concerned about at what point in time are these occurring. And that informs you if you can compare something or not. So A and C are comparable, but not to B. So here's line segment A and line segment C. They each have their own unique endpoints. So at T1, we create this vertical line, which looks like our x-axis and for time. And we create this vertical line, and we look to see where it intersects. Is that any endpoint, so here, T1 all the way up to the top, at any point, would it cross line A or line C? And it does. So we can compare line A and C, but not B, because at T1, it is not comparable. It does not have a point that intersects this vertical line. The second terminology unique to this section is at T1, A is above C. So again, on this line segment, A comes before C. And when I say comes before, we look at the endpoint ordering. So if A and C ended together, we would go to the first point to determine. But here, A is above at this segment. Line A intersects the line above line C. So A is above C. And this is the terminology here. This symbol is the above, and the T1 designates at what time interval this occurs. So if we had another time segment out here, you would have a different intersection. You'd have a different line segments to compare to. And here's a little bit further example. We pass, when you order by sweeping, you pass from left to right. Now the book has some pseudocode on page 1025, but that pseudocode is very general to give ideas about insertions and other points. So I feel it's a little more useful to look at the graphical example here to really relate the point that how time is functioned into this algorithm. So again, the x-axis is treated as time. Time for this algorithm is if you were to sweep through all intervals of time. Actually, it doesn't really determine on time, it determines on the number of line segments that you have. So n is the number of line segments, again, base 2, and the lowest runtime is n squared, where n is the number of segments. So here we would have 3 segments, so 3 log base 2, 3 is our uppercase, and our lowercase is 3 squared, or 9. Having this methodology, you can see at different time intervals, we have a different set of comparable line segments and a different, in this case, which ones are above each other. So at T1, or T1, is above line C, and it's also comparable. Now, line B is above line C, but not comparable at T1. So now progressing to T2, extend the vertical line up, and now you intersect 3 lines because a unique point is found along the vertical. And now we're looking at the ordering. So which one came first? So A endpoint came before the B endpoint, which came before the C endpoint. So A is above B, which is above C. So again, this relationship shows the order of intersection here. If you go to your next time segment, T3, you can see now A no longer extends or has points along the A line segment no longer intersect the vertical line of T3. So now only B and C at T3 are comparable to each other. So in T1, A and C are comparable, and at T3, B and C are comparable to each other. So this algorithm lends itself to some other basic ideas of time scheduling and event point schedules. So when exactly do these occur and at what times actually becomes important, which is very good for ordering or queuing events. Stated before, other ones just simply look at if the point exists or does not exist in a set of points. They don't actually consider at what time do they occur so that we can compare some if we can determine if they're comparable or not to each other. One thing that is not in this example, but obviously could happen, is that you have 2 lines intersecting times one is above the other. So that's another interesting point to note because time changes which is above or which is below and which is comparable. So again, in this algorithm, it's not so much the time frequency that plays an issue with the run times, it's the number of line segments that you have that you must evaluate. Because as one has a fixed endpoint, you'll be able to calculate the intersection of the two again. And we'll review the definition of intersection is if the segment straddles the line, so if it crosses the vertical, here as A crosses T1, or an endpoint of one segment lies on the other. So if B had started on T2, it would also count as an intersection. So it still fits our previous definition of intersection.